Okay, we're going to be talking about applications of derivatives, applications of these slopes of tangents, and it's actually really neat because physics requires a lot of derivatives. Economics requires a lot of derivatives. So it's fun to kind of look at this kind of stuff. So let's take a look at the first example. We're going to look at two examples here. It says for a motorcycle traveling at a speed v in miles per hour, and when the brakes are applied, it says the distance d in feet required to stop the motorcycle may be approximated by the formula d equals 0.05 v squared plus v. It says find the instantaneous rate of change of distance with respect to velocity when the speed is 44 miles per hour. So, I want you to think about this. Who in the world would even use this kind of math? All right? If you've ever been pulled over by a police officer for speeding, the police officer stopped you with a radar gun. They clocked your speed at an instant. What has happened there is that the police officer took the derivative with their radar gun. There's calculus involved in that. Okay? That instantaneous speed, that instantaneous rate of change is just what made you guilty. Okay? So what we're going to do is we're going to write out what we know, and that is that we've got some function dv, d of v, all right, and it is 0.05 v squared plus v, all right, and let's see, do they tell us what v is? It's the velocity, so this is v, all right. The distance is what we're looking at, d, and the distance over time is what's going to give us our speed, our instantaneous rate of change, our speed. All right, we're dealing with miles, so the rate of change is going to be in miles per hour. All right, so let's take a look here. If I've got that for my d of v, and I want to know then what d of 44 is, because again, remember our formula, our limit of our difference quotient. All right, it is going to be d of 44 plus h minus d of 44 all divided by h. That's what we're doing here to find that instantaneous rate of change. So what I'm going to do is I'm going to plug in the 44 into my formula so that I can get the distance at 44 miles per hour, how far I've traveled. All right, so I do that, and it's actually not plus v, it's plus 44. Okay, there we go. All right, I'll let you do that on the calculator, all right, and you're going to get something that looks like this, 140.8, I believe. Now we're going to look at d of 44 plus h. So we're breaking it apart step by step. All right. It's 0.05 times 44 plus h, quantity square plus 44 plus h. Something like that. I'm going to write it over here. I'm going to do the binomial expansion. It's not too much fun. I mean, unless you can square large numbers in your head, right? 44 squared is 1,936. Oh, I just did that in my head. All right. Plus 2ab, 2 times 44 times h, 88h, okay, plus h squared. All right, we get something that looks like that, plus 44 plus h, and now I'm going to distribute. And when I distribute, I get something like 0.05 times 1936 is 96.8. 96.8. Then times 88 is going to be 4.4h and then it's going to be plus 0.05 h squared plus 44 plus h. And I'm going to, yet again, combine like terms. 96.8 plus 44 is going to give me 140.8. Imagine that. Okay, 140.8 plus, let's see here, 4.4, no, not 4.4, 5.4. I was like, I knew there was another h. 5.4 h plus, and then it should just be 0.05 h squared. Okay, so this right here is the f of 44 plus h. Maybe long-winded, but it's okay. Now we find the limit of the difference quotient. F of 44 plus h minus f of 44, all divided by h. Now I'm going to use what I know. This right here is this right here, and this right here is this right here. All right, I'm going to substitute the values that I have, and I'm going to have 140.8 plus 5.4 h plus 0.05 h squared minus 140.8, and as suspected, that cancels out. I divide everything by h, and what do I get? The limit as h approaches 0 of 5.4 plus 0.05 h. That thing right there goes to 0. I am left with 5.4, and the units are miles per hour. Okay? Because it's the rate of change of the distance over time, and it's an instantaneous rate of change. So this is the instantaneous speed. So let's say that, I don't know. I'm trying to think. I mean, you may think it doesn't make any sense, but that's the rate of change of the speed at that point in time. Okay? When you've traveled, 44 miles. All right. So that's one example. Okay? That's one example. Now let's take a look. Okay? And let me go ahead and write in also. This is the instantaneous rate of change. All right, let's take a look at another example here in just a second. So let me move this around. Okay, so the power P in W, watts I suppose, generated by a particular windmill is given by this function P equal 0.015 v cubed, where v is the velocity of the wind in miles per hour. Find the instantaneous rate of change of power with respect to velocity when the velocity is 7.4 miles per hour. So definitely a neat application because wind energy is, getting to be such a big deal. All right. So let's see here. I'm going to say that my P prime, all right, because P is 0.015 v cubed. My P prime is going to be 0.045 v squared. I'm just letting you in on a little secret. What do? All right, this is what you do. You multiply this by that, and then you subtract 1. This is the power rule for derivatives, but that's going to come a little bit later. But this is really neat. So this is our P prime right here. All right, so let's just save time. We've used a shortcut already. You can definitely do that right there. But let's just leave it at that. All right, we've saved some time. We took a shortcut, if you will. All right, so there's our P prime. All right, what we're going to do is we're going to find P prime of V. All right, and what was V? 7.4. So I'm going to say 0.045 times 7.4. All right, to the second power. I plug that in. I'm going to get something like 0.045 times 7.4 square, which is, okay, forget it. Let's just do it on the calculator. No sense in writing it all out. Let's say it's about 2.5. Okay, so 2.5 miles per hour. All right, that's actually our answer here. This is the instantaneous rate of change of power. All right, with respect to the velocity. All right, so instantaneous rate of change. All right, now if you are wondering how in the world did I get this, I'm going to write out the work for you. So let me pause and then I'll come back with all of the work. And I won't explain it or anything, but you'll be able to see it at least, and you can pause it then. Okay, so this is the rest of the work. I found my P of V here. I found my P of V plus H here, which was a really tedious little binomial expansion. I plug that in there. I plug that in there, which ends up being all of this minus all of this, all divided by H. Combine like terms, and again, that's what I knew I was going to end up with. Again, I had told you all at the very beginning that this was what was going to be expected. But otherwise, there it is worked out. You might pause it to study this, all right? But I'm going to tell you this. Don't worry. There are rules for derivatives that are coming, and you're going to love them. So for now, I hope this helps. If this was helpful, remember, like and subscribe.